really, this is technical education, basically, right?
Yeah, and that was really what he had to deal with is what the heck is a PLA?
What date on that?
This would have been 75 when it was announced, right? Well, that came out when it was announced in 75, right?
Yeah, but that was not the only thing that we did. If you look at the back of that, there is a little envelope, and in that envelope there's something in there that I did that I earned the name of Snake. It's like remember Kaplan, Ralph Kaplan?
Oh, of course I remember that.
Yeah, right.
Oh,
And what I did, we had, there's even a photo of the die.
That's great.
Remember this? I don't see this.
Well,
To Ralph, see,
no.
this thing here.
Yeah, was I submitted for press release in July of 75.
Yeah.
Issue of EDN. Okay.
Right. You see, I submitted this photo. Okay.
Yeah.
We didn't have First Silicon yet for the press release, so I sent this thing in. There's no die inside. I just put a label on it.
Perfectly acceptable,
At the time, yeah.
marketing activity.
Yeah.
No
And
problem.
then there was another issue, EDN. Now let's see, was it Electronic Engineering Times? Let's see, what was that type?
George Rusky.
Yeah, the George Roski thing. So George Roski, we present this paper, and he then later took the half part of that paper, where it talked about the device description, and he published in EDN. I mean the ED in September of '75. Okay.
I have a copy of this, but I didn't have the front page.
Yeah.
So this brochure.
Yeah.
Oh, did he run this whole thing?
No, he ran half of it,
1975.
okay?
Yeah,
And then EDN, in the following year, '76, ran the second part of it in the, in here. You can see some of the drawings, you see this kind of stuff. It's the application side of it.
Right, right.
You see it, if you look more in it, you will probably see it somewhere.
What's really interesting is that the applications, the memory applications that you talked about, so memory overlay, core patching, and subroutine addressing, which is the early...
They were trying to, for the people that didn't know what a PLA was, they were just trying to associate in their mind something that you could do with it. And of course,
So these are all good stories. How do we get these incorporated here?
Yeah, I mean, that's right. We need to. Well, hopefully they'll actually come up as the storyboard winds out. So.
Yeah. Okay. You see
could
this?
start-
So this you have here,
Okay.
and then there was.
Right.
I mean,
Table.
so the term programmable logic didn't exist, and I don't think you ever used the idea.
Anyway, it was the second part. It is embedded in here, and so that it happened then in two separate events. That one after the article went 1 year, and the other one was in April of the next year.
So the interesting thing is that a lot of this work seems to be the date seems to be 1975.
Yeah.
So that means that the device design didn't start in 1975 because
No.
Right. So 74. That's why.
Was it 73 or 74?
74.
It was definitely
Because
firmly
it-
rooted
well,
in
yeah.
74.
Because the breakpoint was when we got a yielding workable 4K PROM. That was the density. It was really a density issue. We knew what kind of process manufacturing density we needed in order to be able to make this. And we were having problems making the 1K PROM work. And so I did a new design of the PROMs and used the 4K as the starting point. And when that 4K worked, I told you I saw Lionel the other couple of weeks ago. And he remembers very well when that 4K worked, it was, okay, we're going to redesign the 1K based on that 4K. And it was all about PROMs at that time. But once we got that working, that enabled this to be able to work.
But were you already working on the 4K at the time? I thought at the time that I came, okay, the 1K.
Well, the 1K had been
Had been done.
Well, it had been done over and over and over again. It had been done a couple of times.
Yeah, it was
71.
Oh,
So it was
because-
the 82S115 that I designed in '73, late '73 or early '74.
Yeah.
And when that thing worked,
Okay, because from what I remember, I joined in '75, I think, or '74, the end of sometime like that, and I started working on proms. FPLA wasn't even the purview yet, and
No,
from my
no,
okay. And then I remember that the problem that I was really going to solve at the time was the yield on the 1K, which is the 82S126.
yeah.
And then you're saying that at the time that we had that yield issue with 126, the 4K was already out?
The 4K came out the end of '74 or early '74.
Okay.
And it was based on a different approach. Now, the 1K before the 1K prom had been using an emitter array, and manufacturing issues with the yield, the defect density for the emitter array was just tremendous. At the same time, we had a Schottky diode 256-bit prom, the S123, that was yielding fine. But the key was how did we get enough voltage in a double decoded. The 123, you could come right in from the output, and you didn't have to decode the columns. But to get to a 1K, you had to have a column decode, and the question is how, with the breakdown voltage of the process, how did you get enough voltage across the fuses in a Schottky diode array? So they kept trying to make it with an emitter array, and the yield was terrible. So I figured out a way back, column SCR, what you mentioned before, came up with that for the 4K design, and found that we got good yield, and we were able to do that with that design approach. And immediately we did a Schottky diode version of the 126, and that was the story of it was Jean de Grenier, who you remember, Sandy.
She made my wedding dress.
That's right. Well, she took the 4K design and made a 126 version of it in 1 week, and she laid it out in 1 week. It was fabbed in 1 week, and in the following 2 weeks, the 256-hour burn-in requirements, it was released to production. So from start of layout to release to full production was 4 weeks. At the time, after the 2 weeks, when we made the masks for the 1K, Lionel, instead of just starting an engineering run and getting it out, he started 1,000 wafers based on those masks.
Wow.
And he still remembers that. When I saw him, he still remembers that bet.
I bet he does.
So, and because we were in such bad shape on the 1K prom from a customer commitment and sales and all of that point of view. But anyway, so when that 4K and 1K worked, that's what.
Well, that fits right in here in this Signetics FPLA precursors in 1974. It says proms, right?
Yes.
So you should tell that story there. This is the setup that allowed us to do that, right?
And I'll if I can, I'll talk a bit about the technology limitations and the nichrome fuse, the dual layer metal process. All of these were requirements in order to, and that'll be the theme from my point of view, is the technology enablers that have to come in to be able to say, okay, now with this technology we can do something really interesting that nobody else was able to do.
Right.
So in the storyboard we actually separate the precursors are independent of Signetics, if you will, and then the
technology
are all coming into the intersection of. So it's a separation of. Let's talk about the world independent of Signetics initially.
Okay. And that's Napoleon.
Yeah, well,
Napoleon.
in those days, basically they were using standard logic, not TTL logic.
So 7400 series at that point?
Pardon me?
7400 series?
7400 TTL series was a standard core product available to the designer. Okay.
Right.
Then there were some ASIC products, but these ASICs, they're kind of different than the way we look at them today. The ASIC product of the day was what?
Right.
Custom peripherals, the 808, 8008 and the 880, you can call them that. And then there were other components that, you can look at the ROMs, you can look at an ASIC, but it was not really ASIC, it was more of a standard, but these were the precursors of the high density of the future. Okay?
Well, also, I think Mead and Conway's book hadn't been written at this point, and that helped to distill people's views on methodology for ASIC design. So that's another reason why ASICs wasn't the same way as they are today.
Yeah, no, it was just an infant technology,
Sure.
okay? And then there were, if you will, diode fuse matrix products, like Harris had these fusible links combined with diodes, and I used those. I used those myself in 1967.
It's almost a
okay?
precursor to
Right.
Actel, which you blow it once and you can't.
No, you can't. No, they were really precursor to proms because they had a fusible a nichrome link, just like but they're just diodes. There were no buffering. You have to do the input buffer and the output buffer. It's not linear select way, so there was no decoding, nothing. And in fact, I even designed a program for those parts with all kind of fancy lights and switches. Okay. And then there was the mask programmable array from National. It was essentially an FPLA. It was not F. It was PLA mask program. And you could specify a custom code. They would make it for you, but it was very inconvenient because it was not alterable in the field. So that was really the scene, the tools in the toolbox of the engineer.
Now you mentioned another word there, which I think is really important. You said the word tools, and prior to this, we've been talking about silicon and precursors to silicon. But tools at the time, for example, there was no IBM PC for simulation.
That's right.
But it's almost worth stating that because people won't be able to relate this necessarily because the PC didn't come out until much later, and the process, as you said, was
right. Yeah, I think I was planning to mention that when you were asking to the software tools
yes, I think you're right.
for PLDs, and at the time there was no IBM. In fact, from 1975 to 81. There were no PCs, okay?
That's right.
Now, some users had access to mainframes, on-site or off-site, but it was very difficult for them to get to a program table, convert it in some kind of format. They could, card or paper tape, input in, and then wait for, to get a result. It was very...
You're right. We actually have two sections here. One is on the tools that you use to construct programmable logic, and the second section is what the customer used to design for programmable logic. They're very distinct, so we'll get on to that.
And that's the kind I was particularly addressing now. From a customer point of view, they had nothing like that. Okay.
Right. So what was the design?
Well,
the design mindset in the designer's mind.
Well, the designer's mind, for handling our parts. I mean, if you dealt with a microprocessor, you would use their tools, the development tools. For us, it was basically logic tables, program tables. They use Carnot maps, and that's it. I mean,
but that's how they designed their boards with their TTL also, wasn't it?
Right, it was exactly the same way.
But there was no support for optimizing, minimizing Carnot
No,
maps,
there was they had to do it by hand. And besides, once you got to be about six variables or so, it was a very difficult thing to do. Now they used the Cline-McCluskey method to do that, but that it was hard to do. Some people were very smart in segmenting the table, then doing minimization to size and then combining, but it was difficult. That's why we went into the log min, which in retrospect was not a very smart choice we made at the time.
So let's do that in the section on the development tools.
Right.
Sorry, Andy.
You have when we get into that section, I can prompt you for what development tools were out there before you start talking about that. So this section will be the precursors outside of Signetics, as we've done, and then we move to the Signetics field programmable family and how did that start. And I didn't see in here anything about the story about Honeywell that you told me.
Well, so talking with Napoleon and also talking with John Campbell, who was the design manager when I came into the company, and he said that proposals for FuseLink PLAs or like this had been around for a while. They would get requests from their customers roughly once or twice a year, and because of the complexity aspect, they were just never even considered. And remember, I came in 71 as a junior engineer, So I didn't even know about these up to the point that you joined the company. I wasn't even aware of them. It was concentrate on fixing the problem,
Right,
right?
right.
And distracting somebody like me with something sexy like this, it wouldn't have. So that's why I didn't know about it. So about the time that we were able to consider it was when I saw turned out to be the most recent of a bunch of these requests. So people knew the mainframe, the big iron guys knew what PLAs were. They used them as micro-instruction decode to drive their state machines inside their CPU at the time. They knew what PLAs were. They just wanted a FuseLink or a field programmable version of those. That was something that they understood that they needed. And like Napoleon said, the national part was out there.
Right, and I believe, I think that was the seed that was used on architecting our part, because they had 96 product
They
terms.
had 96 product terms as a straight PLA.
Yeah,
We
and-
couldn't do,
and
you wanted
because of the
96,
width- the
you
width
wanted
of the chip.
96, couldn't
Right.
do it,
Right.
couldn't even
So
fit it into
then-
that big honking package.
What was the national chip? I'm not sure.
It was just a straight PLA, okay, which had an AND array or array at 14 inputs and 8 outputs, and that's it. Not even a chip enable on it.
So how did it differ from the 82S100?
Well, the 82S100 has
Yeah.
16 inputs
Sure.
and 8 outputs and had a chip enable. And I wanted a chip enable. That was one of the issues. Yeah,
And that was the big fight.
Yeah.
Was because at 28 pins, this expensive ceramic package was the only thing that we had.
Yeah.
At 24 pin, you could at least go SIR-DIP if you needed the thermal issues. And that's what the national part was in. But he fought for the 28 pin, and that was really what made it feasible from my point of view.
right.
So the national part was still programmable.
Mass program.
Mass,
Mass
not
programmable,
field.
That's right.
And
That's the point I'm trying to get to.
Yeah.
Is I'm
And
just not
from a history point of view, you might want to say, why 96p terms? Because that was how many characters there were in the Hollerith.
Hollerith, yes. Okay. Punch counts.
Hollerith decoding.
Yeah, that's fine.
Okay.
That's fine.
So would you tell that, that precursor, when we start that section, could you talk about, there would have been a number of requests, and, you will have already gone through the technology.
And I didn't know about it until this last one, about the time that Napoleon came in. But at that point, I don't know how you shift from we may have to go back and forth from a technology issue point of view versus the precursors of what made programmable logic interesting. I mean, I think.
Well, from the precursor point of view,
you had a history that you brought in, and an understanding that nobody else had at Signetics.
Right. Well,
these-
I was familiar with what was going on in the field because I had read articles, not because I had played with those. The only parts I played with were the Harris diode matrices. Okay,
Sure.
which are small things, and the PLA was just reading articles that talked about them, saying, "Oh, well, these are interesting products."
Yeah.
But the involvement and the motivation wasn't there to do anything until the internal motivation came, because Ron showed up with this idea of this device, and then we said, okay, well now, all right, how do I compare what we want to do with what is out there, and that then we said, okay, we got to change things, and Ron, I think the trade-off of the 96 versus the 48, you must have made when you looked at the
Well, I started doing die size calculations.
right
And power calculations.
Right.
And speed, power, cost, those were the trade-offs in those days just as it is now. And talk a little bit about that, but also the enabler, what was the key was Signetics had this history, even with yield problems, of emitter arrays.
Yeah.
We knew we could make them if they were small enough, and then the combination of being able to do a Schottky diode array and an emitter array on the same part, that was really the key
right.
breakthrough, I think.
That's what the same way I felt that when you asked the question, my mind said, what was that? Okay, we had first of all a reliable nichrome fuse. Okay?
Right.
Second, we had design knowledge of how to make an AND and an OR array both fusible, not just having only one array like some competitors could only make. Okay, and we had a designer who knew how to do it.
Right.
And we had a lot of manufacturing experience because these problems are a lot of yield. So all these combination from an organizational standpoint were ideal to get ourselves in that area.
So this, you know, I think the transitions work really well. So if we, you know, we start with the precursors outside, and then talk about, you know, the history of customers asking for this, but it was, you know, and then the whole Honeywell story, and say, but there was no way to act upon it until we solved these problems. And then you can seek into the story about the, you know, 1K versus 4Ks versus, you know, the Schottky versus emitter, right? That these, when we solved that problem, then we were in a position to architect it. Then the next section is, well, what was the architecture of this? You can talk about what you just talked about. I played with different things. I had the idea, I came in the company, and I brought this, you know, set of knowledge. So I think all that flows right, you know, right together.
So that seems to work, yeah.
I think so, yeah. So as it's written here, I think what you guys just said maps really nicely onto this, and, you know, and you can make the transitions work really smoothly.
A couple of small points, just to make sure the reader or the viewer, you kept saying other people had PLAs, but they had mask program PLAs rather than field program PLAs. That's quite an important distinction, I think. So if you can remember to say that.
I'm sure.
Do you think the reader will remember?
Yeah.
I don't know.
No, we'll remember.
Yeah, you'll remember that. The other one is,
what's
the intersil reference? We skipped over that one because I know
that's... And that, by the way, that's what I was when he was talking about Harris, I was confusing with intersil. Harris was fusing. Intersil was, they had this gold-doped old process, and they tried to make a field programmable PLA.
And this is the one I'm talking about, it didn't quite...
Similar to National, a 24-pin part.
It was an exact
48 P terms.
It was an exact copy, except it was 48 product.
Exact copy of the national part?
It was an exact copy,
Right.
Yeah,
but was masked.
except it was 48 P terms.
48 products and field program.
And it was slow as blazes because it was on this old, even by then, old process.
Right.
Old doped, it was like 90 nanoseconds.
Did they push that out into the marketplace and try to sell it?
Yes, that was actually released to production, but it failed.
But it failed.
Because, one, it only had 14 inputs instead of a full 2 bytes.
Right.
It did not have the chip enabled.
Sure.
And it was slow. So those combinations killed it.
Let me make a comment on the flow over here that you were suggesting. I think that if we stick with the outline here, I think run entry would be very well with the technology problems to solve. When the question is asked, what were the technology capabilities advantages? Okay, so now in a global way, I'm referring you to here with this reliable fuses and the IEL-PROM process. But then Ron can say, well, but you know, the details are the fact that this what I had done with solving all these process things and the design things. Okay.
That goes to a question, Andy, that I need your input on, because I can talk for 5 minutes on just the nature of the nichrome fuse and why it was important to be able to program it in a certain way, and what that basically involves is if it's programmed quickly, the nichrome doesn't go anywhere. It was only 450 angstroms thick, and that what happened was if it was programmed quickly, the whole fuse basically liquefied and pulled apart and left a clean gap. If it was programmed slowly, then it was allowed to have local hotspots within the nichrome, and you'd have little openings that would pull apart locally, and then you'd end up with this sponge-like material that would have very tiny gaps, high fields that could grow back. But the nature of how it programmed was something we finally discovered in trying to figure out what the yield problems were. But that's more of a materials process technology thing. It's fascinating to me, but I don't know, it may be a sideline to this whole thing.
Yeah, I'd say I wouldn't spend 5 minutes on it. I mean, you know, you have to talk, you know, this is one of the things that made this possible. You know, I think it's worth, you know, that hey, we got here because we could do this, and there were these issues, but I wouldn't talk too much about the materials.
Okay.
But you certainly throw it in for sure as an enabler, as you said.
So, because you know, this is the computer history museum, right? So they like to talk about the computer side of things as opposed to the material side. So, when you were talking about the you used the term big iron guys. Please use that term again. That's good. Because it ties to the computer history theme, right?
But let me interject a point though from what he's talking, because that leads to a funny story. You know that then if we don't talk about it, we won't. But because of what he's saying, okay, I remember when I went to the field to show how I had identified that problem in the data I/O programmer, that the voltage that was not getting clamped and causing the output structure to blow. Then I said, okay, now I have all these parts and I have this little program with me. I show the people, how this is done. And when before going in with salespeople, we went out in a bar at night, and some of the guys stole the parts that I had to present. So when I went there to do my show, I went there, took the program, and the part there were no parts. So the customer thought it was all planting. So I was worried, and Mike Ackworth was there. I don't know how I survived that. I said, Napoleon, what have you done? What do you mean, what have I done? They had stolen because they had all these customers, that were waiting for these parts. But here's the issue: on the same piece of board, it was like one of these pieces of foam that you black foam. I had also put some customer returns, military customers, they were asking for this regrowth of fuse. I said, I want you to take this into reliability back at the plant and give us a report. So they stole everything. So I had those things, and so I couldn't reply to the customers. And so I had to say, do you know, 3 years later, okay, a bunch of parts showed up on my desk from a sales office somewhere in Connecticut. I said, hey, I find these parts around. So there must be somebody that was all aware of what had happened, and finally was making good on that. But anyway,
that's a great story. Whenever you want to interject that, just find the right place.
The human interest part of this really.
Well, maybe that's the point where I can, if you make some comments on these reliability things.
I'll set it up.
So we're at the second page out of 20, and
so we'll have a lot to talk about. That's okay. We got all day, when it comes to doing it. So we described the 82S100 FPLA architecture and interface. So how did you start the architecture? What was the architecture like? Would be the question I would be asking. What went into thinking through the architecture?
The architecture of the FPLA at its core was quite simple, because what you really had is a bunch of gates mixing with a programmable matrix. Okay, but we had to decide how many of these end gates. We used to call them product terms. Okay, and we had to decide how many there were, and our decision of how many was really a design issue, because they couldn't fit into the cavity of the chip of the package that we were looking at. And then the advantage that we wanted to impart to the device was the full programmability to the end array, but also feeding the second level logic of the OR. So we had to provide an architecture that could work around the fusing mechanism from both of these arrays. And the number of output we had to choose was, in my mind, it was imperative with a byte size output. I wasn't happy with just 8, because I wanted to really address 2 type of applications. So I wanted a byte manipulation. So you have 16 inputs, 2 bytes in, 1 byte out, and a chip enable, so that I could enable the output on a bus. And output programmability, so that we could have a function when outside, which was either a true or complement of an output function. And that was the basic elements of the architecture. That's how the FPLA was structured.
And why did you have a notion that there were 2 different applications you wanted to use?
Why? Because the way products were being used before, there were large proms, 1K and above, that were being used in more lookup table type of applications, because that's what a prom is. And then there were smaller proms, 32 by 8, even 256 by 4, that were used as logic replacement, where the designer, to consolidate packages, would essentially use the input of the proms as logic inputs. There were 5 on a 32 by 8, and then use each output as a logic function. But that was not very cost-effective way of